Hello ladies and gentlemen, and welcome back to C.A.R. Entertainment. I'm your host Dylan Hamilton, and today we're going to be talking about A22 biology and specifically the Hardy-Weinberg theory, which is a little bit of mathematics. If you're not good at maths, don't worry, we're going to go through step by step how you answer a question through Hardy-Weinberg, essentially what it is and what factors affect it and all. If you get it in the exam and you know how to do it, happy days, easy marks. If you're unsure about it, hopefully this video will clear it up and you will be able to get those marks easy peasy lemon squeezy. So let's go on and talk about a couple of definitions. We already covered them in previous videos, but it's good to just go over them once more because they do apply to Hardy-Weinberg. So a population is a group of organisms of the same species found in a defined geographic area. Phenotypes that will be adapted to the environment will be passed on to the offspring, and these are known as selected for. Non-adaptive phenotypes will not be passed on, and these are known as selected against. The gene pool will describe the sum total of all the genes in a population at a particular time. The allele frequency is the proportion of a particular allele in a population at a particular time, and the genome is the entire genetic complement of any one organism. So, Hardy-Weinberg. What is the Hardy-Weinberg equation? Well, the Hardy-Weinberg equation will calculate the allele and/or genotype frequencies in a population with respect to a trait that shows Mendelian inheritance patterns. So, we need to know the equation, which is P plus Q equals 1. That's the first one. Now, P will correspond to the dominant allele, and Q will correspond to the recessive allele. This 1 you see where it equals to, so P plus Q equals 1. That 1 represents 100% of the population, which means each individual in the population will have 2 alleles, either 2 dominant or 2 recessive, or 1 of each particular trait. So the individual genotype equation. So this is how you find out the genotypes. That's for alleles, this is for genotypes. In terms of individual, if your frequency is homozygous dominant, you use P squared. If the frequency is homozygous recessive, it's Q squared, and heterozygous is the 2PQ. So the frequency of individuals of different genotypes is expressed in the equation P squared plus 2PQ plus Q squared equals 1. So this 1 again stands to 100%. So the P squared, that's the amount that are homozygous dominant. The Q squared is the amount that's homozygous recessive, and the 2PQ is those that are heterozygous. So if we go into a question such as, in a population size of 200, how many heterozygous is for the type that has a frequency for the normal capital W allele and the vestigial wing small w, with 16% of the population being homozygous recessive. So there's quite a lot in that question, but we're going to go through it here. So we know the homozygous recessive is 16%, and therefore as a decimal that can be expressed as 0.16. And we know that homozygous recessive is Q squared. So Q squared is 0.16. To find Q, we just square root that. So that means the square root of 0.16 is 0.4. Therefore Q is 0.4. So when we go through and use our first equation, we know P plus Q equals 1. And we know Q is 0.4. So to get 1, we do 1 take away 0.4, and that's 0.6. So now we know that P is 0.6 and Q is 0.4. So to find out what P squared is, we have to square the 0.6, and that gives us 0.36. So now we know P squared is 0.36 and Q squared is 0.16. So we substitute that into the equation of P squared plus 2PQ plus Q squared equals 1. We know that's going to be 0.36 plus, we don't know what 2PQ is, plus 0.16 will equals 1. So to find out what 2PQ is, we have to have 1 and take away the addition of 0.36 plus 16, or in layman's terms, you will add 0.36 and 0.16 and take that number away from 1. That will give you 0.48, which means that 2PQ is equal to 0.48. Now, in order to actually answer the question, which is how many heterozygous there is, you have to do 0.48 or 48% times the population size, which is 200, and therefore we know out of the 200, 96 are heterozygous. So there's assumptions that the Hardy-Weinberg theory makes, and that is that the population will be larger, because in small populations, random variations will skew the distribution of alleles and genotypes. Mating has to be random because there has to be an equal chance the individual of any one genotype will mate with an individual of some or any other genotype. The individuals must be diploid because the trait has to be inherited in a typical Mendelian pattern. Differential selection because it cannot take place based on 3 genotypes under consideration of all genotypes being equally favoured, and also it assumes that mutations are not taking place and there's no migration. Thanks for watching this video. I've been Dylan Hamilton from C.A.R. Entertainment, and I will see you next time.